OTAS, Unsupervised Boundary Detection for Object-Centric Temporal Action Segmentation. Humans naturally watch and learn from instructional videos. One key component of the watch and learn process is that humans perceive information streams, for example videos, as subsequent event chunks. For example, to understand and imitate a video of making cereals, humans segment it into take bowl, pour cereals, pour milk, and stir cereals. Therefore, temporal action segmentation aims to label every frame in an untrimmed video with action tags. Various learning-based frameworks tackle action segmentation under supervision. Fully supervised methods require frame-level annotation. Researchers also harness weaker supervision such as narrations, subtitles, action transcripts, and action sets. However, densely annotated video datasets are often criticized to be excessively expensive. Even worse, human-decided action boundaries are subjective, leading to non-negligible biases. In the more tempting unsupervised scenario, there appear two branches of works. Clustering-based methods learn to group similar frames and transform the segmentation problem into a clustering process. Boundary-based methods learn to detect the boundaries that indicate the most salient variations among the frames and generate segmentation afterwards. While the current research hotspots are mainly the elaborately designed clustering or boundary selection techniques, a crucial yet less studied component in this field lies in the very early stage of the pipeline, that is, the feature extraction module. Conceptually, we highlight the importance of extracted features in that they fundamentally determine the criteria for grouping or distinguishing the adjacent frames. Existing extractors of the state-of-the-art methods pay equal attention to all the details in the video clip. Thus, the subsequent segmentation might be easily interfered with thematically calculus but numerically dramatic variations. For example, sometimes work ABD fails to distinguish the fine discrepancy between cracked egg and spoon flour as the actions occur in the far end of the camera perspective. Meanwhile, it oversegments fried pancake due to the whole body motions of the human subject. Inspired by the cognitive grounds that humans rely on partial components to segment complex activities, we attempt to alleviate the incompetence of global visual descriptors by exploring the merits of object-centric local features. We propose the framework of OTAS. Given some untrimmed sequence of frames, a self-supervised global perception module learns global visual features. A self-supervised object attention module captures local interacting features and inter-object relational features. Afterwards, the boundary selection module fuses the generated global and local features to detect the salient boundaries for action segmentation. Specifically, ResNet50 serves as a spatial encoder to transform a sequence of k consecutive parsed frames into the sequence of low-dimensional embeddings. Next, a cascading transformer architecture is leveraged to model the latent temporal relations. Several upsampling and convolutional layers are stacked to decode the predicted current frame. To optimize the encoder-decoder architecture in an end-to-end manner, mean squared error is adopted for loss computation. The global visual feature is extracted from the backbone layer at inference. Object Attention Module leverages an off-the-shelf detection model to obtain both interactive region and object masks. The interactive regions pass through the same encoder as that trained via the global perception module and produce local interacting features. Meanwhile, the object masks are consumed by an object relationship model to generate object relational features using graphs. We build an object relational lookup table by collecting the relations from the visual genome dataset, which concern objects concurrently appearing in the COCO dataset. It is utilized to construct a relational graph for each frame, connecting semantically reactive and spatially neighboring objects. The object masks are consumed by an encoder to initialize each node's representation. Then multi-head self-attention is used to process the graph information. Finally, a fully connected layer is applied to compute the object relationship features. The graph neural network is trained by predicting the future frames from both the image features and the cropped object features. During inference time, latent features of the GNN are extracted, known as the object relational features. Given the access to the three features, we define its temporal feature difference as the accumulated squared delta distance between a sequence of k consecutive features prior to current frame and another sequence of k consecutive frames starting from current frame. Local maximums of the temporal feature differences are regarded as the boundary candidates, who vote to decide the final boundary predictions. Another highlight of this paper is a discussion on the evaluation metrics, where we point out popular frame-level metrics such as mean of frames are likely to be manipulated by the dominant pattern in the sequence. For example, in this case, while ABD fails to detect more than 80% of the boundaries, it reaches a high MOF of 56.78 because the MOF is manipulated by the dominant frames standing for cut fruit, marked in purple. While the recognized acceptance threshold of boundary F1 scores is 5% of the length of the corresponding video instance, which is far too coarse, therefore we choose 2 seconds, which is invariant of video length, to illustrate for evaluation of the boundary start of swim powder. It is clear that a 2 seconds deviation is not harmful. However, a 22.3 seconds threshold will cause the boundaries even in background and take plate to be falsely labeled positive. In terms of the recommended metrics, our OTAS outperforms the previous state-of-art approach by up to 41% on average. In terms of MOF, OTAS is superior to all the baselines on the breakfast and 50 salads datasets. As supplements to the quantitative results, we conduct a user study and a qualitative case study, which cross-validate the competitive performance of OTAS and the rationality of our claim on evaluation metrics. Furthermore, by directly consuming raw video inputs, OTAS is found to be efficient enough to perform real-time inference. Thanks for listening.